MacMaths, let's do some maths today. AS Mechanics, Connected Particles, Part A. Okay, so Part A, I'm going to look at simple cases of blocks connected by a string today. I'm going to give you two examples, and I'm going to give you two questions to have a go at. To make this more interesting and more palatable, I've drawn a colourful little spiral there for you. Okay, and I'll leave that on. Okay, hopefully I won't make any mistakes, because if I have to do this again, I'll have to write all that out again because I've just ticked that box. Okay, so here we go. So let's remove that. These are the two cases we're going to look at today. Really simple. We've got two blocks, and we're going to slide those blocks in that direction by a force of, we're going to apply a force of 50 newtons horizontally. In that direction, it's going to drag those along, and then we're going to flip it up. We're going to pick it up by a piece of string and lift it up as well. Okay, so that's going to be my second example. So let's have a look at this. And when I'm talking through this example, I'm going to show you how you do all of these sorts of questions. The first thing that I always want you to consider is, when you've got connected particles, I want you to try and consider whole thing, the whole thing. I want you to try and consider the whole thing. So by that I mean, this is, because this string is going to be tight as you pull it along, you can treat that as a whole unit. You can treat it as 6 kilograms being pulled along by 50 Newton force. Okay, so that makes sense. But I also, on all of these, I want you to, where possible, okay, is consider separately. Okay, so we're going to do that on all of them, you know, as we go through all of the lessons. Consider the whole thing, and consider the blocks if there's more than one separately, or the car and the caravan, you know, that we've talked about in the introduction separately. So we're going to either look at this, or we're going to look at that, and just the forces acting on just this or just that. Okay, so those are the two things that I want you to do. I also want you to draw in your diagram, you know, the important forces. Okay, so in this string, whenever you get something with a string or a rod in, we need to put the tension in. Now tension, you know, acts away from the object. Okay, so tension is actually a retarding force on this 4 kilograms. It's being pulled this way by a force, you know, but actually this dead weight of 2 kilograms here is pulling back that way. So this, we always add tension acting away from the object. That tension is also pulling this 2 kilograms along in that direction. So for this 2 kilograms, the tension is acting away from it. So the tension is in that rod is going to be acting away from the 4 kilograms, but it's also going to be acting away from the 2 kilograms when we look at those separately. So always put that in. Okay. So let's do this one then. Okay, so in this question, what we're going to do is we're going to find out the acceleration, and we're going to find out acceleration, and we're going to find out B, the tension that would be in that string. Okay, so the acceleration, we're going to first of all consider the whole thing. We're going to apply F is equal to ma. And by considering the whole thing, of course, this 50 newtons is pulling 6 kilograms. Okay, now I said that we weren't going to use friction. It's, you know, and we're not in the whole this year going to use friction. So I'm going to say that this, in the exam, it would say this would be on a smooth surface. We will look at a situation with friction in at the end, but a simple one. But we're going to say it's on a smooth surface, like ice. So there's going to be, we're going to say that there's no friction. That doesn't really exist. You know, even on ice, you know, you pushed it, it would eventually sort of slow down and stop, wouldn't it? Wouldn't carry on skidding forever. So we're just going to, it's one of the assumptions that we're going to make, that the friction is so small, we're going to ignore it in this model. So the only force pulling them here is 15 newtons, and there's no frictional forces acting that way to slow them down. Okay, so it's just one block. So the net force is just 15 newtons. There's no other forces involved here when we consider the whole thing. Okay, so that's why considering the whole thing, you know, it can make it easier. And the mass of the whole thing is 6 kilograms. So you can see here that 15 is equal to 6a. Divide both sides by 6, and 15 divided by 6 gives you 2.5. So the acceleration is 2.5 meters per second to the minus 2. So that will, if that was smooth ice, it would accelerate in that direction at 2.5 meters per second. The tension in the string now, okay, so this is where we consider them separately. Now we can consider either one of those. I'll show you for both just for this first one. The easiest one is this one here, okay, because there's less forces. This one here, if we consider this 2 kilogram force, the only force it doesn't know what's going on over this side, it can't see over the block. So the only force that's acting on that is the tension. So it's the tension that is pulling that along. And we know that it's accelerating because it's a tight string at the same rate as the whole block. So it's accelerating at 2.5 meters per second squared. We've just worked that out. So if we consider it separately and just apply F equals ma to this, okay, we can see that the force is the tension, and it's equal to the mass, which is 2, times the acceleration, which is 2.5. And we can see that the tension in the string then is 5 newtons. Okay, so now we know that the tension in that string is 5 newtons. So when we're using setting up something like this, we have to make sure that that string will withstand 5 newtons, because if it won't, if it snaps, then this whole system won't work. Okay, let's just say we considered, let's find the tension again, but let's consider just this. If we consider the 4 kilogram block, okay, now acting on that, just considering that, what have we got? We've got 15 newtons acting that way, and we've got the tension acting that way. So those are the two forces acting on that block. And we know that it's moving at an acceleration of 2.5 meters per second squared. So if we applied F equals ma to this, we can see that the net force moving that along, because it's moving in that direction, is 15 minus t, isn't it? It's whatever's left over when you've taken t off the 15, that's the one that's driving it. Okay, that has to be more than t. So the net force, we've talked about that before, that's pulling it along is that minus the bit there. And that's equal to the mass times the acceleration, so times 2.5. And you can see here that we've got 15 minus t is equal to 4 times 2.5 is 10. Okay, we take the t over there, take t off, you can see that that the tension is going to be 5 newtons. So it doesn't matter when we take them separately, which one we use. Okay, I always use the trailer or the caravan, and when we come to those questions, because it's always a bit simpler, the maths. There's only one force to deal with rather than 2 forces to take into consideration. Okay, so that doesn't come simpler than that. Let's just turn it up on its head there, just lift that up now, and we're going to apply a force, acting up. What we're going to do is, now that we've worked out that the 2.5 acceleration is 2.5, let's lift it at 2.5. Okay, let's just change this question round. So let's lift it at 2.5 meters per second squared. Okay, so it's going to now accelerate up by a force that we're pulling it. Now we've got tension in the string here, and we've got a force that's pulling it up at this particular acceleration. So this time I want us to find A, the force that would pull it up at this acceleration now, and B, the tension again. Right, by lifting it up now, okay, the weight of these were acting on the surface, but there was no friction, so that didn't affect our model going horizontally. But now it's moving up. Remember that weight is a force, so mass times gravity is the weight of something. That's a force acting down. Now that means that we've got here mg, mass times gravity. That is 2 times, that's the mass, 9.8, and gravity is 9.8 meters per second squared. And here we've got mg acting a force down from this block here. So this block, this 4 kilogram block is creating a force, a weight of 4 times 9.8. Acting down. We've also got tension. So tension, I'm drawing those arrows in. So two forces of weight now acting down from that block and that block. Tension is acting away from the 4 and acting up away from the 2 kilograms because it's pulling that 2 kilogram weight up, and we've got the force here at the top. So a lot more force is involved in this one. Okay, so let's do the same thing. Let's consider the whole thing. Well, this force, okay, is pulling, the whole thing is pulling 6 kilograms up. That's what's happening. Okay, so we can treat this as one mass of 6 kilograms. Okay, so what is the net force that's pulling it up? Well, the net force, because it's going up, it's the force pulling it up, the net force pulling up, minus any forces acting down. And any forces acting down is the weight of this whole system, which is the 4 and the 2, which is 6 kilograms, times 9.8, mass times gravity. In other words, these two bits added together, 4 times 9.8 and 2 times 9.8. So the weight of this whole thing, okay, acting down, this is overcoming that force, that's the net force, is equal to the mass, which we know is 6 of the whole thing, times 2.5. Now the M here is 6 kilograms, isn't it? It's the whole thing. So the force minus 6 times 9.8 is equal to 6 times 2.5, and 6 times 2.5 is 15. So the force is equal to 15 if we add 6 times 9.8, whatever that is, to both sides now. There we go. Let's do that on my calculator. So we've got the 15 and we're adding that to both sides. So if I do that, I've got 15 add 6 times 9.8, and that gives me 73.8. So the force is 73.8 newtons. There we go. And the tension in the string, okay, so consider them separately. So I'm just going to consider this B separately now. I could do it for A, I've just shown you that, but I'm going to do it for B. So if we consider that separately, there it is. What's acting down on that? 2 times 9.8, that's mg. 2 times 9.8, and what's acting up? Acting up is the tension, and that's 2 kilograms, and it's moving up at 2.5 meters per second squared. So if we apply F equals ma, the net force pulling up, so this is the driving force that it's moving up, so the tension is bigger, has to overcome the weight, doesn't it? Okay, and that net force pulling it, is it because it's moving in that direction, is T minus the 2 lots of 9.8. Now I do that lot, so it's that, I know that's 19.6, is equal to the mass times the acceleration, and we know that the acceleration is 2.5. Okay, so there we've got the tension is equal to, that's 5, and we're going to add 19.6 to both sides. So the tension is 24.6 newtons in the string. And I could have considered this and had the 73.8 minus the tension plus mg, okay, the 4.98 is equal to the 4 times 2.8, and it a lot more complicated, but it would have given us the same tension. Just checking that fits in. Okay, so I hope you're okay with that. What I'm going to do now is I'm going to give you 2 questions to do. Okay, so have a go at these 2 questions. I'm going to put them out for you now. I've already written them out. So let's rub those out. So try to think about how I've done that, considering them as a whole thing, considering them separately. Okay, I've done the same thing. Okay, I've got 2 blocks P and Q sitting horizontal, 10 and 5 this time. A force is applied away, and you've got to find the force and the tension. And P is now suspended, and it's lifted up by a 200 Newton force. I want you to find the acceleration and the tension in the string. Okay, so put it on pause now and have a go at those 2 questions. I'll just zoom in on them. Okay, there we go. I'll zoom out a little bit. All right, okay. Okay, if you're back with me now, we're just going to go through these two. So let's go through these two. So this first one, two blocks P and Q sit on a horizontal plane connected by a string. So they'll say things like light inextendable string. So yeah. So there's my 10 kilograms there, and that's P, and Q, there's my string, and that is 5 kilograms. And away from P, so away from P, and they both accelerate in that direction at 2 meters per second. I could have drawn it the other way around, but anyway, there we go. Done it that way around for a change. Find a force is applied to P from Q, that they both accelerate 2. Okay, so find the force and the tension in the string. Okay, so considering the whole thing, so part A, the force, F is equal to the mass times the acceleration. So quite simply, that force is equal to the mass. The mass of the whole thing is 15. The acceleration is 2. So it's simply 30 newtons. You need a 30 newtons force with 15 kilograms to get that to accelerate at 2 meters per second. And B, the tension in the string. Okay, so let's put that on, acting away from the 5 kilograms. Let's pick the simplest case, the 5 kilograms. There it is. There's the 5 kilograms, and the tension is acting that way. Okay, and pulling it along, and it's pulling it along at 2 meters per second to the -2. So we're simply going F equals ma. Okay, the force is the tension is equal to 5 times A, which is 2, so the tension is 10 newtons, tension in the string. And I could have taken that one as well if I wanted to and used the 30 newton force that I'd found out. Okay, P is now suspended, so there's P. This time I've given you the force of 200 newtons, so let's put that in, and dangling down below it. Okay, so we've got 10, we've got 5, and we've got Q dangling down below it, and we've got to find, let's put the tension in, tension acting away from both of those. Okay, and we've got to find the tension in the string and the acceleration. So it's telling us it's going to be accelerating upwards. Now if we did all the maths and the acceleration came out as negative, it means I've done the question wrong, and actually that 200 newton force is not enough to pull 10 and 5 kilograms up. You know, that's acting, the weight of those two is more than 200. It's not, because I have checked the question. So what have we got down? Well, we've got 5G acting down there and 10G there. So what I've done is, as well, you'll see this used a lot. When we say that gravity is 9.8, it's 9.8 rounded off to 1 decimal place. It's very close to that. So if we want perfect accuracy, you know, sometimes questions are just in terms of G. So 10G is perfectly accurate, and then you decide on the accuracy of G you want. It's like calling something 5 pi, isn't it? It's 5 lots of 3.14, and you can be as accurate as you want, but the moment you call it 5 pi, or leave something in surd form like √2, it's accurate. It's only inaccurate when you then, you know, round it off, or we round gravity off to 9.8, or I think in physics you tend to do it 9.81, a little bit more accurate. Mechanics, 9.8 is good for us. Okay, because these are just models. All right, so let's do this. Find the acceleration and the tension in the string now. Okay, so let's find the acceleration first. Okay, for this one. So the acceleration. So let's consider the whole thing. The whole thing. Okay, so we've got F equals ma. Okay, and the force, the net force, of course, is 200 minus anything that's acting down. Now 15G is acting down, isn't it? 10 and 5 make 15. 15 kilograms, the weight is 15 times 9.8 in terms of newtons as a force. And the mass is 15 times acceleration. Okay, so let's just work that out. Get my calculator. 15g is 15 times 9.8, 15 times 9.8. I could do it, of course, do it all in one go. So 200 minus, that's 147, is equal to 15a. So 200 take away 147 is 53, is equal to 15a, and then divide both sides by 15, so 53 divided by 15, and it gives me 3.53. So the acceleration is 3.53. Okay, now I'm just going to check that because when I did that before I didn't get that. So 200 minus 15 times 9.8 is equal to 53, and then divided by 15 is equal to 3.53. Yeah, okay, so I must have done it wrong before. So that's 3.53. That's the acceleration, rounding off. Okay, and we want to find, what else did I want you to find? The tension in the string. So let's consider the simplest one. So let's consider this one here. I hope this can fit on. Let's just check my, yep, I can just squeeze it on here. So I'm just going to do my B here. So this is my 5 kilograms, just checking again, guys. Yeah, 5 kilograms. We've got the tension acting up, and we've got mg, which is 5g, acting down. So this is just this, okay? I'm considering them separately now, just this bottom one, because that's the simplest one. And I know that it's moving up at 3.53, okay? So applying F equals ma. The force, the net force, of course, is the tension pulling it up minus the 5g for this block, okay? Not, you know, not considering anything else, is equal to the mass of this is 5, and we've got 3.53 there. So the tension is equal to 5 times 3.53 plus the 5g. Okay, and I press cancel, so I had the more accurate version of that, didn't I, down? Okay, but anyway, let's not, oh dear, that's on a bit of a slope. Okay, so we've got 5 times 3.53 plus 5 times 9.8 is equal to, and that gives me a tension of 66 point, and I'm going to go, because I've rounded things off, I'm going to drop a decimal place to 66.7 newtons. Okay, I hope you found that helpful. 2 simple cases on a smooth surface with no friction, and then just lifting it up, and you'll get those, you know, you'll come across those cases, you know, on an AS Mechanics paper. Very, very simple. You know, this would be a question 1, as simple as it could possibly get, that one. Okay, thank you. That's part A over and done with.